So let's continue in 12.2. Let's write down this definition. Let U be, we'll just do it in 2D. It's the same in 3D, it's just order right, really. So let's let U and V be U1, U2, V1, V2. So they're both in R2. And K is a scalar, so K is some real number. Then we define, this is the definition of addition and scalar multiplication. So addition of vectors, when we say U plus V, then we mean to add the components. So it's U1 plus V1 and U2 plus V2. Scalar multiplication, we have K times U. So that's going to equal KU1. So you multiply each component by K, almost like a distributive property. K times U2. All right, so that's the definition of scalar multiplication and addition and scalar multiplication. So let's look at what the geometry would look like because of that. So this is the geometry of vectors. So geometry of vectors. So we'll look at scalar multiplication, but let's just talk about first what U1 plus, or U plus V looks like. So when you add those up, we just wrote that down, right? So U1 plus V1, U2 plus V2. So we'll put both vectors at the origin and add them up. Okay, so do this and that. All right, so suppose you had U, maybe looks like this. Okay, and then the sum, and then you have V, looks like this, suppose. So what you're doing then is adding the components. Actually, let me change this a little bit. I don't want it to be the same value there. Let's just go. Let me start over. And I think I'm not sure when I mentioned this to your class, but I'm not going to do a lot of editing. We're just going to roll with it like we would in class. Because it takes very time consuming to edit and do all these videos. So if you're going to add those two vectors together, let's call this U and V. And I'm just going to show you how this works first. What you do is you add the terminal of one to the other. So it would be this sum right here. Okay, so when you add those up, what you get is this sum right there. And so, and I kind of ran out of room. Let me move this down a little bit. Nice thing about this is I can move that around, okay? And then let's fix this. All right, so that's the sum you're going to get when you add those up. So now this is your V. And so what, and this is the resulting vector of U plus V. Okay, so the way that, what happens then is you, and let me show you off to the side here. And so the components look like this. So this value is your U2. This value here would be your U1. So right here is your U1. And then you're adding to it the V2. So this component all the way to here, this distance is your V2. So the sum of those goes from here all the way up, right? And then similarly, the sum out to here becomes your V1. So this distance here is your V1. So this whole thing here then is your U1 plus V1. And then this distance here, right, is your U2 plus V2. And that's your resulting vector, is what you would get. So what you do to add those, let me show you the other way to look at this, is you draw in your vectors like this. So if we have this vector U, this vector V, then what you create is, and I'll show you, a parallelogram. Okay, and then I'm going to paste it. And so you get this, and I'm going to make that dotted. Okay, and then you take this, paste it, and you get that. And so I create a parallelogram. I'm going to erase it. Now you would do the same thing, but you just freehand it, or you'd use a straight edge or something. And then the resulting vector is that diagonal. So that's how you create the sum of U plus V. So the green right there is your U plus V. Okay. Scalar multiple. Let's talk about that real quick here. So if you have a vector, say V, like that, the negative V just changes the direction. And I'll be pasting these. Right, so that just changes the direction of it, like that. And then if you half it, then it's just half of it, right? So you get just this vector, same direction, it's just half. So half V would just be taking half of it, same direction. And then 2V, because I can, I'll just show you what it looks like. You get that. You just get two of them. Okay, so then that's your 2V. So that's what your scalar multiple does. Everything, well, I guess all but this one looks like it's in the same direction. Okay, so that's your half right there. Okay, so what we get are all these properties out of those definitions. So let's write down all those properties. Next, I'll go through them. You pause and write these down. Just because it's in the book, I do not believe you should just look at it and go, oh, that's it. You want to write all these down. Just like we were in class, I would write these up. And just the act of writing it out is important. Okay, so let U, V, and W be elements of Rn. So this is, we're kind of starting the concept of not just 1, 2, or 3 dimensions, but any dimension. So n-dimensional. So n is an integer. N is actually, we will say it's 2, 3, 4, etc. Well, we won't really consider one-dimensional vectors. It doesn't really make sense much. So let's consider vectors to be either in 2 dimensions, like the plane, or 3, or higher. Okay, so n-dimensional is what we mean by that. So the first property here, U plus V is the same as V plus U. That's commuting. It's called the commutative property, back and forth. So if you go back to the definition, back up here, would make sense that you can commute those because inside the vector, each component are just real numbers. So you have the commutative property of reals. So you just commute these back and forth, which would make these commute back and forth. So that's the commutative property. And then similarly, if you have u plus v plus w, you can add v plus w first or u plus v first. It doesn't matter the order. So this is called the associative property. Okay, so it's associative property of addition. Then you have the identity property of addition. So I'm not going to label all these, but u plus the zero vector is just u. This is an additive inverse property. So there's an opposite because inside the vector are all reals. So you always have opposites and you can get the zero vector. This next one is the multiplicative identity property. So the vector of 1, or I'm sorry, it's a scalar, I'm sorry. So a scalar of 1 times u is equal to u. And notice the subtlety here. 0 times u, where 0 is a scalar, gives you the zero vector. So it's still a vector quantity. Okay, so keep track of that kind of stuff. The next thing is associative of scalar multiplication. So you can multiply the scalars first and then multiply by u, or multiply the scalar inside and then multiply by a. Again, this is like a distributive property of a scalar across the addition of two vectors. And then similarly, this is like a distributive property of u across the sum of two scalars. So like I said, we want to keep track of those properties as much as we can. Okay, next theorem. Okay, so this is one we'll use a lot. All right, so next theorem, let C be in the reals and V, sorry, can't write right now, and V be in Rn. Then the magnitude of C times V is equal to the absolute value of absolute value of C times the magnitude of V. So it's the absolute value of C times the magnitude of V. So when you take the scalar out, you got to take its absolute value. Okay, so we're going to do the proof of that. This is in 2D. So let C be in R and V in Rn. So I'm restating what it was up here. You got to restate the hypothesis. All right, so, and we're going to do this, we're just doing this in 2D. So what we get then is V, you can extrapolate to any dimension. It's pretty easy. It's just fewer components. So V is V1, V2. And what we get then is magnitude of C times V is equal to magnitude of C times, and then now write out what V is. It's V1, V2. Okay, so now we can apply the properties above. So now we're going to take the scalar and multiply in, or the definition actually. So back up here. Where'd it go? Here. We're going to take the scalar K and multiply in. So this is C. So we're going to take the scalar C and multiply into the vector. So it equals magnitude of CV1, CV2. So now that that's inside, we can apply the definition of magnitude, which is the square root of CV1 quantity squared plus CV2 quantity squared. All right, so then we're going to factor out the C that's in both terms. and it's squared. So you get the square root of c squared v1 squared plus c squared v2 squared. Okay, now factor that. You get the square root of c squared, and then it's v1 squared plus v2 squared. So now you can rewrite that as the square root of c squared, and then the square root of v1 squared plus v2 squared. So what's this definition of the root v1 v2 squared? That is the magnitude of v by definition. And then how else can you write that? The square root of c squared is often defined to be what? Well, what are we looking for? We're looking for absolute value. So yes, that is the definition, or one way to define absolute value. And then that's, like I said, magnitude of v. And that's what we wanted to show. So we just showed that you start here, and where did we end up? We ended up here, all by definition and properties. That's exactly what we wanted to do to show this statement is true. Okay.